Bismillahirrahmanirrahim. In this video, we'll discuss design of a bandpass RC filter. And this is the circuit for bandpass RC filter, and this is the response curve. So you can see it will allow signal to pass within this band and will attenuate any signal which is prior to this or after this. And we can think of this as actually consisting of two filters. One is a low pass filter and then combination is a high pass filter. So this is low pass and then high pass. And if you look at the response curve, this one is the high pass curve, so attenuating the low signal and passing the high signal. And this one is the low pass at passing the low signal and attenuating the high signal. Just look at this portion only, so don't confuse that we are at the high frequency and how we are saying that this is low pass. If you look at this portion only, then this is high and this is low, so it is passing the low and attenuating the high. Okay, and the frequency between F1 and F2, this is called the pass band frequency, and the difference between the two is called the bandwidth of the signal. Now formula for the frequency is same formula 2 pi RC, but just to distinguish, I'm calling this F1 the critical frequency for high pass filter as F1 or FCH. So F1 or FCH is 1 over 2 pi RH and CH. It is just to distinguish that it is for the high pass filter. Similarly, for the low pass filter, we are calling it F2 or FCL, and this value is also 1 over 2 pi RC, but we are putting L and C to distinguish it. Now the formula for magnitude for high pass filter is as shown here, and for low pass filter the formula is as given here. We have seen these two in the low pass filter and high pass filter videos. Okay, now let's see the example. A signal conditioning system uses a frequency variation from 6 kHz to 60 kHz to carry measurement information, and there is a considerable noise at 120 Hz and 1 MHz. So let's draw this. So we have signal between this range 6 kilo to 60, but we have a noise here at 120 and then there is another noise at 1 MHz, and we are required to first of all design a band pass filter to reduce the noise by 90%. We have to reduce the noise, these two, by 90%. And also we have to find out the effect of this filter on the band pass frequencies. So we'll see this, how to find this effect. Okay, now reduced 90% means actually that the magnitude should remain 10% or 0.1 of its value. First we find the critical high frequency F1 or FCH, which will reduce the 120 Hz by a factor of 0.1. So this portion we have to find F, and this was the formula that we had discussed, the magnitude formula. The magnitude is to be reduced to 10% or 0.1. Frequency, this signal actually we are dealing 120 Hz, so 120 Hz, and for this we have to find the critical frequency F1 or FCH. And if you calculate this, then F1 or FCH will be 1200 Hz or 1.2 kilohertz. So this will look like this. The filter will now look like this. It will reduce the noise to 10%, and its critical frequency where the value is 70.7% or 0.707, also called 3 dB down. So this point is 1.2 kilohertz, which we are calling F1, and also we are calling it FCH, critical frequency of the high pass. Okay, and this is just a repeat. We had found this, the critical frequency 1.2. Now let's do for the low pass filter, and for the low pass filter the frequency we calling is FCL or F2, and this should reduce the 1 megahertz signal by a factor of 0.1. So this is the low pass filter. It would now reduce, or designed to reduce the noise here by 10%, and we have to find this frequency. So we'll follow the formula for a low pass filter now. This was the low pass filter formula. We'll plug in the values. So the F now, F is 10.6. This is what we want to reduce, 1 megahertz. So F is 10.6, and we have to find this frequency, which is F2 or FCL. Here it is written FH. But anyway, when we calculate this, then F2 will be 100 kilohertz. If you do this calculation, and mind it, this is F2. Okay, so we have found out F2 to be 100 kilohertz. So now we have found the two frequencies for the filters. This one 1.2 and this one 100 kilohertz. These are the critical frequencies. Okay, now that we have found the critical frequencies, we can design the filter. So let's do for the low pass first of all, high pass, High pass filter has the critical frequency 1.2. Now we'll use this formula, as you have been using in the previous videos, to calculate resistance. But for that we have to assume a value of the capacitor. So let's assume value to be 0.47 microfarad. Putting the value here, and the frequency 120 or 1.2 kilohertz, the critical frequency. So 1.2 kilohertz, and the capacitor value, we find resistance to be 282.19 kilo. Now this is within the recommended range. The recommended range is that the resistor should be greater than 1 kilo and should be less than 1 mega. So this is within that range, but this is not the standard value. So for this we have to look the table of standard resistances, and from there you can see these two are the closest, 270 or 300K. So let me, I'm taking 300K, you can take 270 and do the calculation, doesn't matter. And so for the high pass filter, this will be the capacitor value and this will be the resistance value. Now we come to the low pass filter. For low pass filter, we have the critical frequencies here, 100 kilohertz. We are here also we are assuming 0.47 microfarad capacitor and calculate the resistance. But now the resistance is 3.39 ohm, which is very, very small. We have mentioned that it has to be between 1 kilo and 1 mega. And this small value is because we are now dividing by 100 kilo. Here we were dividing by 1.2 kilo. And therefore, we have to now find a lower value of the capacitor, or assume a lower value. So now let's see, let's assume it to be 0.47 nanofarad, not microfarad, nanofarad, 10 raised to the power minus 9. And now putting the value 10 raised to the power minus 9, we get 3.39 kilo, which is within the specified range here, but not standard. So we'll pick again from the standard table, and let's pick 3.3. So these will be the two values for the low pass filters. Now we need to verify effect. What is the effect on the desired passband frequencies? So for that, let's see from here. Now this is the high pass filter, and we want to know how it will affect 6 kilohertz and 60 kilohertz, and similarly the low pass filter, how will affect 60 kilohertz and 6 kilohertz. So let's start from the low pass first of all. So effect of low pass filter, to find the effect we have to again use the magnitude formula, and here we have all the values. First of all, we'll put 60 kilohertz for F. FC is 100 kilohertz. So effect on 60 kilohertz, putting 60 here and 100 kilo, 0.857. That means this signal will reduce from 100% to 85.7%. And now we'll see the effect on 6 kilohertz. So 6 kilohertz signal, again putting 6 kilohertz, its value is now 0.998, so almost negligible effect. It's almost 99.8%, which we can say is 100%. And now we come to the high pass filter. So the high pass filter magnitude formula is this one. Here also we'll plug in the values. First we'll consider 6 kilo and then we'll go to 60 kilo. So 6 kilo signal, putting in 6 kilo and the frequency 1.2, we get the reduction by about 2%, its value is 0.98. And its effect on this one, farthest one, so putting 60 here, we can see that the value is 0.9998, so almost no effect on it. So I hope you have been able to follow this, and will be able to design RC filters if it is given to you. If the question says that you design a lossless filter, then we have to use LC filter, and this is how it will look, the bandpass filter. This is the high pass filter and this portion is the low pass filter. So I hope you can search from the internet these parameters. There are many websites which actually give you the calculation, online calculation, direct calculation, so you should follow that. Thank you.